Briefly here, what we have done so far is we've looked at the Dalton model of the atom. We've been looking at what I would call atomic physics so far, which is the basic structure of atoms. We said that since electrons were discovered in the form of cathode rays, that model of the atom needed to be tweaked. It needed to be adjusted to incorporate electrons into its structure, and that was done by Thomson to get this raisin-bun model. So Dalton's model is saying an atom is like a billiard ball. You can visualize it. Thomson's model is saying an atom is like a raisin bun or a plum pudding. Because of alpha scattering experiments, it became abundantly clear that Thomson's model of the atom couldn't explain why very few alpha particles are deflected straight back. That required some very concentrated mass and charge. Why is it very concentrated? Because it doesn't happen very often that an alpha particle is deflected back. It's a hard target to hit. It's a tiny, tiny target. And through some other logic, we decide that since atoms are neutral and since the alpha particles that are scattered are positive, there must be a large positive charge that causes a backwards force on the odd alpha particle. But that also means we have electrons somehow in the atom spread out, because if the electrons were all concentrated in one area, then we would also get alpha scattering because of that. The alpha scattering occurs because of the positive charge, which must be concentrated positive charge. And the electrons are at very, very large distances in some kind of orbit. But that model of the atom needs to be able to explain line spectra. And in order to come to the rescue there, Bohr's atomic model is what's necessary, where you have electrons going from one energy level to a different energy level, and the difference in the energies of the electron are equal to the energies of the photons that are either emitted or absorbed. However, that atomic model is only successful in predicting energy levels for hydrogen atoms, or what we call hydrogen-like atoms. In other words, all of those atoms that are in the group 1A of the periodic table. So hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. And then we get to the quantum mechanical model, which is loosely thought of, I guess, as kind of a electron cloud model. When I drew this in your notes, I just had a slice of it, so it was a two-dimensional picture. But electrons not only appear in different locations to the left and the right and above and below the nucleus, but they could be in front or behind. So there's this sphere of probability of where the electron can be found. Then what we did yesterday was we started looking at the physics of Rutherford scattering and the physics of electrons in circular orbits around hydrogen atoms. So does anybody have any questions you would like me to go over here? Ian?
Why is the electric force equation so similar to the potential energy?
It's a good question. Why is electrical potential energy found using EP equals KQ, Q over R, whereas the electric force is found using KQ1, Q2 over R squared? The most basic answer I can give you is that work, which is change in energy, is force times displacement. So if I take this force equation and I do this to it, what I'm getting is energy and its potential energy. And the fact of the matter is, D and R are the same thing. So one of them cancels, and you're left with R on the bottom. Okay. Other questions? Okay, we're going to move on. Just to note that these problems, particularly the alpha scattering one, but also the one where you have to find the speed of an electron in an atom, are problems that you might see on a diploma exam. They're somewhat scarce. I don't think you're guaranteed to see both of these on a diploma exam, or even one or the other. But you will see them on my exam. So you need to know how to do them. In the meantime, we're going to be moving on today and starting what I'm calling the second part of this unit, which is nuclear physics. So the only difference between the title on the handout that I just gave you and the one that you already had is this says Part 2, Nuclear Physics, and then it also has different objectives at the bottom. Once again, I believe we're going to finish this unit either Thursday of next week or Wednesday of next week, probably Thursday of next week. Come back, have a day or two of review, and write the exam. So what we're looking at today is an introduction to nuclear physics. We have a whole bunch of sprinklings of different things that lay the groundwork for this unit. And they're actually going to culminate with something called binding energy and mass defect. So we have to understand what nuclear isotope notation is used for and how to use it. We're going to be learning about the 4 fundamental forces in nature, and they are not what you might think they are. Or maybe you do know what they are. And then we're going to calculate what's called binding energy and mass defect of a nucleus, or nuclei in general, and understand the relationship between them. So first of all, some definitions. Atomic number of an atom is given the symbol Z, and what atomic number tells you is the number of protons in the nucleus. So when you look at your periodic table, and the only reason I have this hanging periodic table is so that when you're looking at the one I gave you, you might need my help in locating certain things. So, if we're going, well, where's uranium? I can do this. And you can take a look on yours and locate uranium. Speaking of uranium, uranium is atomic number 92. And what that means is every uranium nucleus in the universe has to have 92 protons. Any nucleus that has 92 protons is uranium. It doesn't matter how many neutrons are in the nucleus. It doesn't matter how many electrons are orbiting the nucleus. And that's the symbol Z. You do have to know that that is what Z is, because I've seen on diploma exams lately, over the past few years, they just say determine the value of Z. They don't tell you atomic number. So it's a memory thing. It's that number that determines what type of atom it is. I used uranium as an example, but we could also talk about carbon. Carbon is atomic number 6, and what that means is every carbon atom in the universe has 6 protons. Any nucleus with 6 protons must be carbon. Isotopes, you use this word in Science 10 and a little bit in Chem 20, I believe. Isotopes of atoms are atoms that have the same atomic number, the same number of protons, but the number of neutrons they have in the nucleus is not the same. So, for example, if I were to look at this nucleus, and this isn't in your notes, this is just something for us to look at. This is a nucleus that has 1 proton and 1 neutron. So since it has 1 proton, it's a nucleus of hydrogen. Because the atomic number is 1, because there's 1 proton. This nucleus has 1 proton and 2 neutrons. It's also hydrogen. So both of these have atomic numbers of 1, and that makes them different isotopes of hydrogen. This hydrogen, which we're going to end up calling hydrogen 2, is different than this hydrogen on the right, which is called hydrogen 3. That number, 2 or 3, tells you the total number of particles in the nucleus. These particles, by the way, are called nucleons. So if I say how many nucleons are there in this nucleus on the left, there are 2 nucleons, 1 proton, 1 neutron. There are, on the other hand, in the second isotope of hydrogen, 3 nucleons, 1 proton and 2 neutrons. Now, the atomic mass number, which is capital A, I don't like the way these things are lettered. I wish that atomic number was A and atomic mass number was M, but I didn't make the rules. The atomic mass number, which is A, tells you the total number of nucleons in the nucleus. And that means that for the nucleus on the left, that hydrogen nucleus that has 1 proton and 1 neutron has an atomic mass number of 2, whereas the atomic mass number of the one on the right is 3. Any questions so far? Isotope notation is the way we communicate all of this without having to use a whole bunch of words. The notation is always going to show 3 things. It's going to show the elemental symbol. In other words, it will show CO for cobalt, Cu for copper, Al for aluminum, O for oxygen, whatever the elemental symbol is. And then it's going to show 2 numbers, the atomic mass number up top and the atomic number on the bottom. So, for example, and we're going to fill in this table together, if I have nucleus A and nucleus B, and nucleus A has 92 protons and 143 neutrons, the atomic number is 92, because it has 92 protons. And by the way, you can immediately locate 92 on your periodic table. Now, when you look at your periodic table, I don't know that this is explained in chemistry because I don't know it's really part of the curriculum, but everything seems to be nice and neat down here, except you go from 57 to 72. And in between 57 and 72 is the series from cerium to lutetium. Never even knew that was a word. So those are sometimes called transition elements because they fit in there. They make the transition between the barium and the lanthanum. The same thing with from 89 to 104. There's a whole bunch that are missing. By the way, your periodic table may not go up to 106, or it may go up to more than 106. Is it 106? 103. It only goes up to 103. So uranium, which is 92, you might be looking at your periodic table going, well, where's 92? It's down here. So both of these are atomic number 92, and they're both called uranium. But we're going to add something to that, because the atomic mass number is the sum of the protons and neutrons. So if you were to add 92 and 143, you can do it now in your head or on your calculator. 92 plus 143 gives you 235. So nucleus A has an atomic mass number of 235. If you were to add the protons and neutrons for nucleus B, you get 238, which means the atomic mass number for that nucleus is 238. This is all so far, everybody, about language, about being able to read things on paper and understand what's being said. So we can call nucleus A uranium and nucleus B uranium, but we need some other piece of information to describe what kind of uranium. And we write uranium-235. That's one way to write it. Now, why do I not need to put the number 92 when I say uranium-235? Why is it not necessary for me to say 92 somewhere? Carly?
Because if it wasn't 92, then it wouldn't be uranium.
Right, if it wasn't 92, it wouldn't be uranium. Uranium, you can look up where uranium is on the periodic table and see it's 92. So the 92 and the uranium together are kind of redundant. You don't need both of them to understand what's going on. But when we learn, starting tomorrow, how to write nuclear equations, we do need both numbers. I have seen, and I really don't like it, I have seen this, where it's written like isotope notation, but they don't put the 92. I think, even though you might see it, I think in this course and in a physics class, that's lazy. I think even though it's redundant to put the 92, you should put it. However, there is absolutely nothing wrong with you writing this and this. You don't need to write out the word uranium. I'm sorry, any questions with completing that table? All right. Use the following information to answer the first example. And this is just building up to the introduction to nuclear forces. In the nucleus of an atom, just a random atom, I'm going to be talking about a helium nucleus in a second. A typical distance between nucleons is maybe half a femtometer. And you can look on your formula sheet to find out what femto means. If my memory is right, it means multiplied by 10 to the negative 15. I just remember it because it starts with the letter F. 15 starts with F. So, not all of the protons and neutrons are exactly that distance apart. I'm just saying that's kind of an average, typical distance. But two protons repel each other due to an electrostatic force because they're both positive. And yet we know a nucleus is held together. The only explanation as far as the knowledge that you have so far is that if I had an alpha particle, and let me show you where the protons are, those two protons are positive and yet they do not push away from each other. Well, they do push away from each other, but they don't fly apart. The only explanation would be maybe gravity is strong enough to hold them together. Maybe. That's the only attractive force you know of between two protons. So what this question is saying is, this helium nucleus, which is a helium-4 nucleus, it has two protons, so if you look on the periodic table, it's helium. It has two neutrons, so the total number of nucleons is 4. We can call it a helium-4 nucleus if we wanted to. By the way, we can also do that. This is an alpha particle. Bless you. A helium nucleus is an alpha particle, while a helium-4 nucleus is an alpha particle. But these two things are positive. There's an electric force on each of them pushing away. So we're going to analyze this in detail by showing that the protons cannot be held together by gravity. And we're going to do that by doing two calculations. You're going to calculate for me the gravitational attractive force between those two protons. And that's a very simple calculation. It's G_m_m over r squared. I don't know that you need to write these numbers down. You certainly can. But I do want you to calculate on your calculator how many newtons of force they are attracted to each other with due to the law of gravity. And what you're going to discover, by the way, I put 1.67 times 10 to the negative 27 kilograms quantity squared because they're both protons, so the mass of each is that number. You can multiply it out if you like. I'm just putting squared. And then on the bottom, I have 0.5 multiplied by 10 to the negative 15. I need to square that because it's the law. It's the universal law of gravitation says over r squared. And can someone confirm, or can all of you confirm, that you're getting just a piddly, puny, minuscule little amount of force? Now, it's not fair to judge it as being tiny because these particles are tiny, but 10 to the negative 34 newtons, it's pretty small. So that's the only force that you're aware of that's pulling these protons together. There's a repulsive force. They're both positive. And in any nucleus that has more than one proton, you're going to have positives pushing away from each other. And we can calculate the amount of electric force of repulsion by using Coulomb's law, KQQ over r squared. And this is a series of calculations that I've seen on a diploma exam. After we're done here, I'll tell you how they would ask it. So if you take Coulomb's constant and multiply by the charge of the proton and multiply by the charge of the proton and then divide by that distance quantity squared, you are going to get the amount of repulsive force between any two protons that are about that distance apart in any nucleus. And keep in mind, in something like uranium, there's 92 protons, and they're all pushing away from each other. They're all attracted to each other because of gravity, but as we've already seen, that force of gravity is it's tiny. 920 newtons. Do you get that? Just think about that for a second. 920 newtons. I may have talked about this yesterday. I can't remember. But 920 newtons I did. in regards to forces of alpha scattering. 920 newtons is the force that would be required for you to lift 92 kilograms off the ground. 92 kilograms is a little over 200 pounds. Okay? That's a large force pushing these tiny particles away from each other. And the bottom line is that if these are the only forces between the protons, if you have an attractive force pulling them together that's really tiny and a repulsive force that's huge, we can take the repulsive force and subtract the attractive force to find out the net force. I hope you're not even going to spend time on your calculator taking 920 minus that, because your calculator will say 920. You're removing a drop of water from all of the water on the earth. It's not changing the volume of water, figuratively speaking. What does that mean? It means, and by the way, on a diploma exam, they would ask you this: how many times greater is the electric force compared to the gravitational force? And you would take this number of 920 and divide by this number and get approximately 1 times 10 to the 36, I think. Pretty near. 1.1, 1.2 times 10 to the 36. What that means is there's got to be another force. There has to be some other force pulling the protons towards the protons that's bigger, that's even bigger than that 920 newtons. And that's called a strong nuclear force. And just to cut to the chase for a second, the strong nuclear force not only pulls protons towards protons, but it pulls protons towards neutrons, and it pulls neutrons towards neutrons. And it does one other thing that I will talk about in a second. So this is a table showing the 4 fundamental forces in nature. In any situation where you have any force, whether it's friction, an applied force, it doesn't matter, it is in fact one of these forces. Friction is actually an electric force. It's a force of repulsion of electrons in the atoms on the surface of the floor with electrons in the atoms on the block of wood. It's hard to imagine. An applied force, when I take this remote control and I apply a force upwards to keep it at this height, it's actually a force of repulsion. It's an electric force of repulsion between the electrons in my hand and the electrons in the remote. In fact, theoretically, they're not even making contact. So right now, I'm actually levitating above the floor. Okay, there's a very, very small distance. It's hard to imagine. So what are these forces? Gravitational is the weakest. These are from weakest to strongest. I don't care for this final column. I would rather assign the number 1 to the weakest force in the universe. By the way, these are strengths at nuclear distances. The force of gravity between the Earth and the Sun is bigger than any electric force. I'm talking at nuclear distances, and I'm talking about forces between nucleons. So if you assign a relative strength of 1 to gravity, the electromagnetic force is about 10 to the 36 times greater. That's that number we just calculated. We've actually done this comparison before. You would have to go back to Unit 2 and look at it. However, starting with the weakest, gravity, then the weak nuclear, then the electromagnetic, and then the strong nuclear. Do you see, looking at that relative strength of 1, 10 to the 32, 10 to the 36, and 10 to the 38, that for nuclear distances, gravity is the loser? It's not even close, right? It's so far behind the other 3. The weak nuclear force, which I'll talk a little bit about today, but save for later, and the electromagnetic force are a little bit closer together, but even the electromagnetic force, which is any electric force and any magnetic force, is 10,000 times greater than the weak nuclear force.
Please excuse the interruption. With Caleb Swampy, please report to the office. Caleb Swampy, please report to the office. Thank you.
I haven't talked about what the nuclear forces are just yet, but you need to get used to the fact that there are two nuclear forces. The strong nuclear force, this is the one that we're talking about today. It's the force responsible for holding a nucleus together. So the name of this force that's pulling the protons towards the protons towards the neutrons, and the neutrons towards the neutrons, the name of this force is the strong nuclear force. And it's about 100 times greater than electric or magnetic. So when we go and we look at these calculations that we did here, and we discovered these two forces for the gravitational and the electric, the strong nuclear force is going to be about 92,000 newtons, approximately. But it's an attractive force. The strong nuclear force is always attractive. Are you with me? Always. However, and I realize I'm dancing all over the place with this table, the strong nuclear force only exists when the particles are closer than about a femtometer. So if the distance from one side of this desk to the other side of the desk is 1 femtometer, and I put a proton here and a proton here, they are going to push apart. They're going to push apart here, they're going to push apart here. When I put them here, they're going to push apart because of that electric repulsion, but they are now in the location in space relative to each other where they will attract because of the strong nuclear force. And since that attractive force is about 100 times greater than the repulsive force, if I can get two protons within this distance, they lock together. That strong nuclear force rules the roost at those distances. A couple of other observations. As far as we know, gravitational forces and electric and magnetic forces act over infinite distances in space, which means theoretically there's a force of attraction between my head and the moon right now. They're pulled together. A globular cluster of stars gajillions of light years away from here are attracted to our solar system due to gravity. There are other forces in the vicinity of that globular cluster that kind of negate that very tiny force of gravity. And the force of gravity drops off very quickly due to the inverse square law. But we believe that electric, magnetic, and gravitational forces act over infinite distances. Strong nuclear, less than a femtometer. I'm not going to worry too much about this distance right now for the weak nuclear, other than to say that weak nuclear force acts deep, 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 deep down inside of the nucleus somewhere. Very, very small distances. We'll talk more about that tomorrow and Thursday. Carly.
So the strong nucleus is always attracted. What's the force that repels them apart?
It repels the protons from the protons?
Yes. Just from being...
It's an electromagnetic force. But at distances smaller than a femtometer, even though this force of electric repulsion between those charges is still quite big, 900 newtons or hundreds of newtons, there's another attractive force which just cancels it out. Okay? And I don't want to talk about weak nuclear in terms of attractive or repulsive. That's not the point of it. It's used to explain certain types of radioactive decay. Hang on to your question, though. Finally, for whatever reason, and I think it's the word nuclear, people want to put weak nuclear third strongest. They want to go, oh, gravity, electromagnetic, and then you have the nuclear forces. There's a staggering here. Gravitational, then weak nuclear is stronger, then electromagnetic, which includes electric and magnetic forces, is stronger still than strong nuclear. You were expected to know the order of strengths, and I would say be somewhat familiar with these relative strengths. Finally, if you assign one to strong nuclear, you can figure out how strong the other ones are based on that, and that's where the negative exponents come from. Ian.
How come they don't have momentum or chemical?
Momentum is not a force. Momentum is momentum. Chemical is not a force. Chemical is energy. This is a table showing forces. Forces, energies, momenta are as different as cheeseburgers, hummingbirds, and the color of the sky. They are different things. Chemical energy comes about because of certain forces acting, which would be electric forces, by the way. Chemistry is all about the behavior of electrons in atoms. The reason why sodium chloride is formed is because that extra valence electron in the chlorine atom is attracted to the positive valence. Well, I shouldn't say it that way. There's a transfer of electrons through an electric force from a sodium and a chlorine atoms. The electron is attracted to the sodium. It's pulled over to the sodium, making them both stable, but that's electric in nature. Okay. All right. There's another reason why we're getting into these forces, and it has to do with this strong nuclear force. Now, I'll let you in on a little secret. If you take an electron and you smash an electron, try to break it apart into pieces, you can't. We believe, physicists have believed lots of things that turned out to be false later, but we currently believe, the best theories say electrons are fundamental particles. You cannot, there's no pieces, there's no moving parts to them. But protons and neutrons have parts. And the individual pieces of protons and neutrons are held together themselves by the strong nuclear force. All right. One other little kind of detail before we get into mass defect and binding energy is atomic mass units. Atomic mass units is a unit of mass that's just more convenient to use sometimes. Because nuclei have very tiny masses, masses of nuclei might be 10 to the negative 25 kilograms or 10 to the negative 24 kilograms or 10 to the negative 28 kilograms. Not 10 to the negative 28. That's too small for a nucleus. But they're awkward units. So an atomic mass unit has a certain definition, and this is not something you need to know, but some of you might be curious. Somebody has decided, let's measure the mass of a carbon-12 atom. That includes all of the electrons. It includes, by the way, the 6 protons in the carbon-12 and the 6 neutrons. I know there's 6 neutrons because it's carbon-12. So when this thing is assembled, they've measured the mass of it, and 1/12 of it is defined to be an atomic mass unit, and it turns out that's the number. Okay? And it's on your formula sheet. There's a more precise value. We don't need to worry about those extra decimals. When you look at your formula sheet, I think in the constant section, it's the very final entry. Is that right? Okay. So we're going to be making use of that. If I tell you the atomic mass, I won't even say atomic. If I say the mass of a nucleus is 235 U, you have to take 235 times this number to get the mass in kilograms. Okay. Now we get into putting this all together. By definition, and we don't do this, it's not a practical thing, if you have a nucleus and you want to separate all of the nucleons into different spaces, it's like having a group of students that are arguing and you put them all in different areas of the room. They're no longer together. It's going to require energy, and that energy is called the binding energy of the nucleus. Think of it, even though energy is not a force, think of the binding energy as the energy that's keeping the nucleus together. Okay? The strong nuclear force, I often say, is the nuclear glue. It's what glues the nucleus together. But there's an energy associated with that. However, because the forces holding a nucleus together, pulling between every nucleon in the nucleus, no matter how many there are, that strong nuclear force is acting everywhere. Because that strong nuclear force is, let's face it, gargantuan. 10 to the 38 times more than gravity. Is that the number? It's incomprehensible how big that force is, and I'm trying to jazz it up a bit for you to really get the idea. That means the binding energy is going to be a significant amount of energy for the nucleus. It's not going to be like hundreds of joules, but it's a significant amount of energy for the nucleus. Now, there is a whole branch of physics that I wish we had a unit in Physics 30 on, and we used to, long time ago, like over 25 years ago, we used to have a unit on relativity, because we use relativity in this unit, so we used to learn about it first, and it's really interesting as well. One of the aspects to Einstein's theory of special relativity is that mass and energy are really the same thing. Okay? They're different, but they are the same. What do I mean by that? Imagine that you were, this is an analogy I've come up with that I think does the trick. Imagine that you were on an alien planet. You're an alien. You live in a tropical paradise. You have a very low level of technology. There's no such thing as electricity or magnetism. You haven't discovered any of those things yet. And the climate on your planet is always tropical, 25 to 32 degrees centigrade. And I come down in my spaceship, and I come out, and I pull out a thermos, and I get your attention, get you to stop bowing, because you think I'm some kind of god. And I open the thermos, and I pull out a big chunk of ice. You've never seen ice before, have you? But if I put that ice in the sun, it's going to change to water. And to those aliens, the concept of water and ice, now that they've seen ice and they know what water looks like, they're different things. But we know they're really the same thing. They're just different forms of that thing. And what I'm telling you is just like we can take liquid water and turn it into solid water, which we call ice, and we can melt ice and turn it into liquid water, energy and matter work the same way. They're related to each other in the universe. This is a hard thing for you to wrap your head around because it's non-intuitive. It's as non-intuitive as the ice-water thing is to the aliens. They've never seen it before. You've never seen this before. There are many applications of this. One application is that when objects move faster, they're more massive. That's one application. That's not what we're going to be talking about today. And I literally mean if you have a proton that's moving fast, its mass is greater than it would be if it were at rest. I don't mean all of a sudden there's more protons to it. The other aspect, though, is that any mass has an equivalency in joules. This E equals mc squared is probably the most well-known science formula in the world and the least understood, relatively speaking. What this formula can be used for is to calculate an equivalent amount of energy that corresponds to a mass. So if I rearrange it, any energy has an equivalent mass of that. C is the speed of light, by the way. What this means, and we're not talking about kinetic energy here, is that when the energy in a system goes up, the mass goes up. So this is true. When I run faster, I'm more massive because I have more energy. When I take this thermos and I lift it to here, it's more massive here than it is there. The difference is negligible. If you were to find the energy I've given it here and put it into E equals mc squared and calculate m, you wouldn't get a noticeable mass. However, when you separate a nucleus into its nucleons, you have to add a lot of energy, a significant amount of energy, because you have to overcome the strong nuclear forces. And when you add that energy, you add mass to the system. This is crazy. I know it is. It doesn't make sense. But it's a fact. The sum of the masses of the separate nucleons will be greater than the mass of the assembled nucleus. What does that mean? It means that if I have a nucleus that has 2 protons and 2 neutrons, and I determine the mass of this thing, and then not perfectly, you get the idea. I do this, and I measure the mass of this and this, and this, and this, and I add those numbers together, I get a bigger number than the mass that it had before I separated it. Because the masses of the nucleons are tiny and the energy required to separate them is large, that increase in mass is measurable. And the mass defect is the difference. So however much the mass changes by is called the mass defect. However much energy is required to pursue that task is called the binding energy. So the binding energy is the energy required to separate a nucleus into its nucleons. The mass defect is how much the mass goes up by in that process. Visually speaking, I'll come back to that in a second. If this is, and I'm using an alpha particle here, if this is the energy in the system, and you might see diagrams like this in Chem 30, except it's chemical changes, not nuclear changes, where you would see maybe H2O, and over here you'd see O2 and H2. You guys do those diagrams? Okay, good. Over time, if I want to accomplish this task, I have to apply a force, a huge force, to overcome that strong nuclear force. And that means I'm going to be adding energy to the system. But what I'm saying is that is the binding energy. And what I'm also saying is, in terms of mass, you'll notice this graph is scaled differently, right? This is a mass graph. This was an energy graph. You don't want to compare the two. In terms of the mass goes up as well. And that mass increase is called the mass defect. So this is a change in mass. This is a change in energy. And when you look at your formula sheet, you see the equivalence of E equals mc squared as delta E equals delta m c squared. And this will be under, I believe, quantum mechanics and nuclear physics. Ian.
When the protons and neutrons are separated from each other, how does it takes energy to get them to that state, but do they have energy associated with them at that state?
Yes, what we would say is they have, but we're not going to analyze this. We would say they have nuclear potential energy. So the work that I've done does go somewhere. Keep in mind, we don't actually take nuclei and tear them apart. We're going to use this idea to explain concepts like fission and fusion and radioactive decay and electron capture and all these nuclear processes that cannot be explained unless we understand that if you took a nucleus and tore it apart, you would be doing work, which would mean you would be adding energy, and all those nucleons have more mass because they all have more energy. Your question is, where's the energy? Call it nuclear potential. Just like when I lift the thermos above the table, I've done work. Where is the work stored? Because work is a transfer of energy. The energy's got to be somewhere. It's gravitational potential. The difference is, and this is interesting, if I let this go, it's going to bond again to the table on its own, right? If I take these nucleons and I let them go, the protons are just going to fly away from each other because they're repelled, and the neutrons will just kind of randomly move around. The reason why they won't go back together is you got to get them closer than a femtometer, right? So this energy that's added is the energy to get them a femtometer apart, so the strong nuclear force doesn't work. All right, let's do some calculations. I will warn you right now that it is so easy to get an incorrect calculation result because even though I say these masses that are changing are significant and the energy changes are significant, you need lots of decimals to appreciate them. And for some reason, even though there's lots of decimals, it seems like it shouldn't matter. It's easy to enter them incorrectly when there's more decimals. The other thing is, when doing nuclear calculations, you are going to be using the mass of a proton and the mass of a neutron that are given here. So the mass of a proton is a little bit less than the mass of a neutron. And what I would say to you is that has something to do with the internal structure of a proton and neutron. Remember I said they have parts to them? Well, their parts are different. We'll leave it at that for now. It gets pretty complicated, and we'll learn about that later. First question. The mass of a helium nucleus is given as that. What is the mass defect of a helium nucleus? Well, what we need to know, you know what? I have to change this. It should say helium-4 nucleus. It has to tell you which isotope of helium it is. So the first thing you want to appreciate is that if it said helium-4, that means this is the state of affairs. It's 2 on the bottom because that's helium, 4 on the top because that's the total. And then you need to be able to say that this contains 2 protons. Why? Because this is the number of protons. It also contains 2 neutrons. Why? Because because 4 minus 2 will give you 2. I'm really having trouble with my highlighter here. Let me try that again. I mean, I think you get it, but I hate to start something and not finish it. So that's what's going on there. And you need to be able to do that no matter how small or big the nucleus is, because what you need to do now is take 2 times the mass of a proton, 2 times the mass of a neutron, so that you can compare that total mass of the pieces separated from each other to the mass of the assembled nucleus. So what I'm going to calculate here is the mass of the separate Is that even supposed to separate? It is, eh? What a weird looking word. The mass of the separate nucleons, which will be 2 times the mass of a proton plus 2 times the mass of a neutron. And I'm not going to write that down. Those numbers are right at the top of your page. You can do this calculation on your calculator. You know, obviously, if I gave you some kind of written question or you were in post-secondary doing some kind of an assignment, you would want to show the substitutions. 2 times 1.6726 times 10 to the negative 27. That's the mass of a proton. It's been almost a full year, but can you just double check? I think I got that right in my memory. And then plus 2 times the mass of a neutron, 1.6749 times 10 to the negative 27. Mind you, if you mixed up the 2 masses, in this case it wouldn't matter because there's 2 of each. So I get this number, 6.695 times 10 to the negative 27 kilograms. Do you get the same number? Okay. So what is the mass defect? The mass defect is the difference between that and never mind. Is the difference between that, which is a bigger number, 6.695 times 10 to the negative 27 kilograms, minus the 6.6443 times 10 to the negative 27 kilograms. And this is going to give us the mass defect of that nucleus. .07 times 10 to the negative 29 kilograms. Okay, so the mass defect, the answer to this question is 5.07 times 10 to the negative 29 kilograms. That's a pretty tiny amount of matter that somehow has been created. And by the way, when you count all of the particles when they're together, there's the same number of particles and types of particles as there are when they're apart. So when I say the mass goes up by a certain amount, I'm not saying something has been added. There's not another particle there that's accounting for it. It's just that everything is more massive. Part B, what is the binding energy? Well, delta E equals delta M C squared. So when the mass goes up, the energy goes up. This energy increase is called the binding energy. The mass increase is called the mass defect. So all we have to do is take this mass defect and multiply by the speed of light squared. .563 times 10 to the negative 12 joules. I don't care about significant digits. That's not my point in this lesson. Are we getting the same number? Is that a large amount of energy? You wouldn't think so. Convert it to electron volts. Is it a large amount of energy? It's a huge amount of energy. This is one nucleus. This is the energy associated with one nucleus. 28.5 million electron volts. C, what is the binding energy per nucleon? This is often something that you're asked. I'm going to go electron volts per nucleon. So we're going to take that total number of electron volts, which is 28.5 million eV, divided by 4 nucleons. I'm going to, at the very end of this lesson, after the next example, explain what the significance of binding energy per nucleon is. But we're going to divide this by 4 and get 7 point something. 7.13 million electron volts. Million eV per nucleon. If you wanted to, you could certainly calculate the joules per nucleon, and sometimes you were asked to do that. And number 3, the mass of a uranium-235 nucleus is given as that number of atomic mass units. Don't forget, one atomic mass unit is 1.66 times 10 to the negative 27 kilograms. I'm sorry, not don't forget. Remember that this is on your formula sheet, right? So the first thing we really should do is convert that to kilograms. And the reason is going to be that the mass of the nucleus needs to be in kilograms because we're going to want to compare its mass to the mass of all of the parts, which we know in kilograms. So if I take 235.043930, The standard practice, by the way, in printed numbers is when you have more decimals than 3, you leave a space so that you can read them more easily and not make a mistake. 043930 times the 1.66 exponent negative 27 gives me this number, 3.9017 times 10 to the negative 25 kilograms. And what I'm going to do is store that in my calculator as A. I want to access all of the decimals. I know on all of your calculators you can probably just scroll up and grab it. So this is the mass of the nucleus. This is the nuclear mass. However, the mass of the nucleons, and what's implied there is the separated pieces, well, I have to figure that out. It's uranium-235. How many protons in uranium-235? 92, sure. 92 protons. Carly, how can we find out how many neutrons?
Subtract.
Sure. 235 minus 92 gives 143, I think. Okay. I'm not going to write down 92 times the mass of a proton plus 143 times the mass of a neutron. That's something we can do on our calculator. 92 multiplied by the mass of a proton, which is 1.6726 times 10 to the negative 27, plus 143 times the mass of a neutron, which is 1.6749 times 10 to the negative 27. I just want to step back and look at my numbers before I hit equals. We're okay. 3.9339 times 10 to the negative 25 kilograms. You will notice that that is slightly bigger than the mass of the assembled nucleus. So the mass of the separated nucleons is more than the mass of the assembled nucleus. The binding energy, the mass defect is the change in the mass. So you just have to subtract these. Just take the bigger minus the smaller. And I get 3.217 times 10 to the negative 27. Still in agreement on the numbers? If I was, this is unfortunate the way Physics 30 is set up, but if I wanted to know the mass defect in atomic mass units, I have to convert everything to kilograms so that I can do the work, and then I have to go back to atomic mass units, because you're not given atomic mass units for the proton and neutron. So now if I take that and I divide by how big one atomic mass unit is, I get about 1.94 atomic mass units. You get the same number? Okay, good. .94. If I want to find the binding energy, the way Physics 30 is set up, I have to use this formula, but I have to use standard units. So I have to use the mass in kilograms. This was the mass in kilograms. I multiplied by the speed of light squared. Why the speed of light in the formula? Because that's what works. That's the way the universe is. 2.90 times 10 to the negative 10 joules. Very quick point here. Delta is final minus initial. I didn't draw your attention to that before, but that's what we were doing. We were taking the final mass after it's separated minus the initial, which means that this delta E that we're finding is a final energy in the system minus the initial energy in the system, and we get a positive number. I want to draw a comparison between this and Chem 30. When you have a positive delta H, you use H for energy in chemistry, I believe, right? When you have a positive delta H, that's endothermic, and that means you put work into it. The energy's gone up. That's exactly what's happened here. If you convert that to EV by dividing by the number of joules there are per electron volt, you get a whopping, well, 1.8 billion. 1.8 times 10 to the 9. Can you look on your formula sheet? I'm a little embarrassed. I should know what 10 to the 9 is. I think it's giga. Or in the words of Doc Brown from Back to the Future, giga. But it's 1.81 giga EV, or giga EV. What is it per nucleon? Let's go with the electron volts. We need to divide. I just want to get back to where we were. This many electron volts by the number of nucleons in the uranium. What was it, uranium-235? There's 235 nucleons in uranium-235. So we're going to divide by 235. And that's 7.7 million. 7.7 million EV per nucleon. We're done the lesson, we're done the examples, except I want to explain to you what this energy per nucleon means. The bigger this number is, the more stable a nucleus is. Can you just look back? What was it in millions of EV per nucleon for the helium nucleus? I want to say 7.13. Okay? So this is for uranium-235. Helium-4 was 7.1 million EV per nucleon. On average, in uranium, there's more energy holding the nucleus together per nucleon than there is in helium-4, which means uranium-235 is more stable. It's held together tighter. And something that we're going to see later on in the course is this graph which shows binding energy per nucleon for a number of different elements. And this iron-56, of all of the elements and all of the isotopes of the elements, iron-56 has the highest binding energy per nucleon. And that means it's the most stable isotope of anything in the universe. It's held together tightest. And this stuff here and this stuff here aspires to become more stable. Smaller nuclei undergo a certain nuclear process called fusion to turn into nuclei that are closer to that pinnacle of stability. And larger nuclei undergo something called fission to break apart to approach that ideal stability. All right, I am going to get you started on your work. Page 33 of the handout, 1 to 7. I think if you get down to 4, you're good enough. I think 5, 6, and 7 might introduce atomic mass units. You could probably get away with doing every odd question. I need you to practice it.